Hello everybody, Mikael here, and I'm gonna talk a bit about algorithms, design of them, and how to think in general when we're solving problems. And I'm gonna provide you with a few techniques, or let's say tools, that might help you when you are sort of trying to break down a problem into a solution and finally get into programming code. So this is my agenda. I'm gonna start as an introduction to talk about problem solving in general as a whole, just to sort of get the environment of this problem solving. I do think it might be helpful sometimes. And I'm going to talk to you about Polya's problem solving techniques, 4 steps to have in our back on our mind when we are solving the problems. And then we're going to review a couple of methods, techniques for problem solving in the computer area. And it's going to be top-down, bottom-up, pseudocode, and flowcharts. So let's start with problem solving on the higher level. So sometimes I get sort of students coming to me when we are sort of they're working in a lab, they're writing code, and they just can't figure out how to solve a problem or troubleshooting or so, and they might get real stressed on this. So sometimes, not always, but sometimes I tell them to take a walk in the park, sort of sleep on it, or get a cup of tea or coffee and just go out, chill in the sun, take a walk in the forest. And all these things is a way for me to say that start breathing slowly and allow for your brain to sort of slow down. And when it slows down, the brain will usually help you start thinking, and it will start arrange the problem into getting a structure of it, and putting the problem into context, and you will see the small bits and pieces eventually that is sort of building up this large problem. So that is my way of sort of helping students sometimes solving problems. But so how can we help the brain to structure this problem? How can we help the brain to think about these problem solving issues? Well, for sure, large and unclear problems, they are real hard to deal with. So no matter how we do it, but we should mostly try to sort of organize and divide these large and unclear problems into smaller problems. That is general good tactic. Smaller problems are sort of they're easier to deal with. You can grasp a small problem. I can solve this small problem and this small problem. But when I have 20 small problems and put them into a large problem, then it's usually much harder to actually sort of figure out a solution for it. Sometimes when you have divided these large problems into these small problems, you will eventually see that some of these small problems are not really problems, so they can just go away. You can just ignore them. Maybe that doesn't happen when we are going to develop an algorithm, but in general, it happens. So, well, it's good to know. Divide them into smaller pieces, easy to solve, might even go away. But to be able to do this, we need to understand the problem. And that sounds like an easy task, but it's really where thing goes wrong eventually. We did not have the basic understanding of the problem. We need to start there. And some things we can do when we sort of trying to understand it is that sometimes it will help when we put the problem into context. So in what type of surroundings, what is the actual context that this problem lives in? So in what sort of area should I solve this particular problem? It could be helpful to understand the context. It can also be helpful to understand when we deal with the semantics of the problem. Semantics here being that me and my friend does interpret the problem in different ways. So we're having sort of different semantics of the problem, and that might be a sort of larger issue when we're trying to understand the basics of the problem. So put it into context. Know when we are dealing with semantics, which could be important, sometimes not so. We could also ask these two questions at the bottom here. Are we solving the right problem? And to know that, we need to understand the basics of the problem. We need to understand, is this actually the right problem we are solving? It is quite fair to ask yourself that question when you are in the middle of this and discussing it with your friends. Is this really the right problem we are solving here? We could also, hopefully, when we have we have the right problem and we have the right context and we are now sort of aware of the different semantics, but we have straightened it out. But now, at the last there, are we solving the problem in the right way? There might be many different ways to solve this problem. So are we solving this particular problem in the right manner? So, few questions that is quite fair to ask yourself and your team when you're trying to understand this. Let's talk a bit about how defining the problem. Is the problem well defined or is it ill defined? How good is how good is actual the requirement specification you are reading? Is it a good written requirement specification? And it could also be a fair question. The writer of this requirement specification, how good are him, she, they, that team? Are they sort of good enough to write the requirement specification? And all this sort of turns down in the material that I got in front of me. Is this really a good and well-defined problem they gave me? Or is it ill-defined? An ill-defined problem might be much harder sort of to solve, and you even don't solve it in the way that the sort of the writer of the spec wanted you to solve it, because it was not too good defined. So this is also important, and we are still here in the cases. We need to understand what is the actual problem that we are going to solve. Well-defined problems, you can hopefully see them when you have them in front of you. They have very specific end goals, very clearly expected solutions that are very easy to read and grasp and understand. So they are sort of maybe crystal clear in what is expected of this type of solution for this problem. Ill-defined problems might lack a few or all of these features. It's not so easy to understand what is actually what are we actually targeting here. If we have well-defined problems, they will for sure allow for more initial planning than the ill-defined problems will. When we have this ill-defined problem, well, we need to deal with it to get a better problem description. And we can also ask ourselves at any time, is the thing we're talking about, is this really a problem? Or is this some kind of discussion that we should just throw away? This isn't the problem we're talking about, so remove it from the equation. And one way to sort of ask these be a bit critic about when you do this discussion. One way to do this is to have this ask the 5 whys when you're in the middle of it. And 5 whys, that is sort of a it's a way of solving problems, or it's a way of finding out the actual root cause of a problem. That is, trying to sort of solve the right issue. And it's just by asking why 5 times. I just want to show you an example of it, because it's sometimes when you are in the middle of things, it might be sort of a bit. I should just go and do it. So there we go. Are we actually solving the right problem here? It's good to ask these questions. So this is the example of the 5 whys tactique. So this is an example. The vehicle will not start. Okay, why? Someone asked. Oh, well, the battery is dead. And when someone says the battery is dead, then it's time to sort of ask and continue asking the questions. So the alternator is not functioning. Why is that? The alternator belt was broken. But why is that? Well, it was beyond its sort of useful service life and wasn't replaced. But why wasn't it replaced? Oh, the vehicle was not maintained according to its schedule. Ah, so that was the root cause of why the vehicle did not start. We did not maintain it correctly. The 5 whys are one way to sort of identify a problem, or the actual problem, or the actual root cause of a problem, in a way. So I still find that this could be somehow useful when you're trying to solve a problem, even in a programming language like we are then. Okay, so we're still on this high level, and I'm just gonna sort of talk shortly about these two. This is basically linguistics, but it helps us understand the discussion we have with our friends when we are doing problem solving. So, pragmatics in this way, that is how context contributes to the meaning of problem solving. So, we would sort of talking about pragmatics, we're trying to put the problem into its context. And when we do that, that might help us understand the problem, and it provides some meaning to what we are actually sort of doing. What should we do here? What are the right things to do? Semantics, that is when we sort of interpretate the different words or meanings in a requirement specification or a problem description, and we sort of interpret them in different ways. And when we do that, and we sort of agree on what is the right way or not, that will also, this semantic discussion might also help us contribute to the meaning or solving the actual problem. But it could be good. Sometimes semantics is good to know. Sometimes it's good to know that we are actually talking about semantics here, so we can just, it is not important. But semantics and pragmatics, just good to know that stuff we talk about when we sort of deal with solving problems. I'm going to wrap this up on the higher level by just reviewing some of the different areas where problem solving is made, and that is in general what we do all day in all different areas that we could work in. So here are some of them. When we talk about problem solving in psychology, that might be finding solutions to problems encountered in life, daily life perhaps. Cognitive science, that should be the research on how people do problem solving. Mathematics or logics might be problem solving where we formally prove solutions to problems. Engineering, that might be finding out new products or processes, could be inventions, or it could be prevent failure of some kind of process or products. Problem solving in the military science, what would that be? Well, they often talk about what is the end state. What is the end state we want to reach here? So we need to be very firm about the end state. And then we can find out several sort of ways to reach it. But we have to have this end state. So I do think sometimes that just relating to problem solving and problem solving, how it's done in different areas, that might help myself think about how myself do problem solving in the computer science or software engineering areas. So it's just a helpful tool. Sometimes, what is the end state? What is the actual end state where we want to be reaching? Sometimes we just need to be sure of that. Okay, so let's move on. We go into problem solving and we are finding out a bit about the techniques for well-defined problems. Well, they are not so always well-defined, but even ill-defined problems we need to sort of solve when we're working. I'm going to go through this Polya. So this is a problem-solving technique. It was released in a book back then, large years ago, 1945. The book was named How to Solve, and it was getting quite popular book, released in a lot of languages and 1 million copies or so. You can read more about it there. So Polya is, well, he's saying that the easy stuff for us here. He's saying, first principle, understand the problem. Okay, yeah, of course. Second principle, devise a plan. Make a plan. Okay, good to know. He says the third principle is carry out the plan. And the fourth principle would be look back, see what you did, learn from it. Maybe we just say that, okay, this Polya guy is stating the obvious. But if we just stay here for a minute and dive a bit deeper into what he's actually trying to tell us, let's see if we can understand it a bit more. So, Polya 1, we must grasp the problem. And here are a couple of questions we can ask ourselves when we are in this sort of problem-solving issue. Do we understand all the words that is used in stating the problem? That is an easy question. Sometimes we really don't understand all the words. We just say we do. So, do we do it? If not, maybe we do not understand the problem completely. What are we asked to find or show? What are they actually saying? You should do this. Is that clearly stated? Can we restate this problem with our own words? If we can't do that, well, did we really understand the problem? Or when you try to say, your friend, can you restate the problem? And then you restate the problem. Did you restate it in the same way? Or do we have a sort of semantic issue here, how we interpret the problem description? So when we put these sort of questions here, I think we get a firmer checklist that, well, understanding the problem is not really easy at most times, perhaps. Can we think of a picture or a diagram that sort of could represent make it easier to understand the problem? Is there enough information here? Or is there lacking some information to enable us to find a solution? That is also very not too uncommon, that a requirement specification is lacking information. So we need to sort of interpret it into someone. What are the meaning here? Could we decide for ourselves? So everything here, it is not, in general, that easy to really understand the problem sometimes. So don't underestimate this Polya 1. The Polya 2, he's just saying, okay, now you got it, devise a plan. So we need, from all the different plans there, we should sort of select a good and proper one. Polya says there are many ways to solve a problem. So he's giving us a short list here. It says, okay, you can guess and check. You can look for a pattern, you can make an orderly list, you can draw a picture of it, eliminate all possibilities, you can solve a simpler problem. So don't take this hard problem, just solve a smaller one of it. Use symmetry, use a model. Build a model to solve it. Consider special cases. Yes, that might be good. Work backwards. Okay. Change it around. We work backwards. We can reason about it. We can use a formula. We can solve an equation. We can be ingenious. We can really be creative when we are trying to solve this and devise a plan for it. So many different ways. And yeah, we can work in an engineering fashion according to a nice set of method, process, how to deal with this. But we should not forget that problem solving and finding ways to move ahead could also be very creative. Even if we are part engineers, we are also part creative people when we are working in a sort of programming development environment. So the Polya 3 says that carry out the plan is much easier when you have passed section the Polya 2, creating the plan. You should, he says, follow through with care and patience, and sort of if you have the necessary skills. Sometimes you don't have the necessary skills to carry out the plan, and that could be good to know the stuff that we are uncertain of, that we need to sort of deal with along the way, or we need to learn new stuff along the way. Those could be sort of important parts to know about. He also tells us, go with a plan, stick with it, persist with it. And when you are for sure that the plan fails, so discard it, get a new plan and move on. Don't be misled, so stay online, keep your focus, don't be misled. It's so easy to go astray when we're working with this and, oh, this sounds interesting, let's go on this way. No, let's stick on the plan. Okay? What Polya 4 says also, and this is basically what will make us become better problem solvers. When we have solved one problem, we will become better. If we solve 10 problems, 20 problems, we will become even much better if we always try to learn from what we did. So look back, reflect and look back what we did, what worked, what didn't, and sort of bring this with us and build up your own strategy for problem solving in these areas. As time goes by, as you learn, when you solve a problem or you didn't, learn from it. That is what Polya 4 is telling us. And a Mikael tip on Polya would be that when so you have Polya 1, 2, 3, 4, but if you're actually going to work them through in some sense, it wouldn't be too bad suggestion to do a document of it. Write it down and use the headlines, Polya 1 to 4, and write them down as headlines, and below each headline you just write what you're actually sort of thinking on doing, and you're sort of breaking it down into these 4 Polya headlines sections. And this could be good. It's sort of like taking a thought of your head and putting it into a document. And this is also a way to sort of relieve some stress from your mind. You know you have it in a document, so I don't need to think about it right now. So, and it will also be a good way to sort of look back. Okay, I have my Polya document. What did I write down here? Oh yeah, we did that and that decision. Okay, yeah, maybe we should have gone in that direction instead. So it's a good learning document when you look back. So if you have a large problem and many people in your group, work it through. Make a document of the sort of the Polya 1, 2, 3, 4s. Perhaps we should look back now. try to think about some problems that you did solve lately. Did it turn out well or not? Why did it not turn out well? Ask yourself, did you really understand the problem before you went ahead and solved it? Maybe, maybe not. What were the issues anyway that worked well or not? So bring all this with you onto the next sort of problem solving journey you're taking to. Okay, so I'm soon gonna show you 1, 2, 3, like 4 different hard techniques that you can actually think about and use when you are sort of solving the problems. But first, let's stay with the philosophies here. This is basically some kind of can talk about software philosophy here. And I've labeled a few, 1, 2, 3, 4, 5 different items that sort of can help you discuss and relate when you're solving a problem, or you're solving, implementing application, solving a requirement specification, and deciding on what features you are going to do. So the first up there is a Yagni, and that's basically saying you ain't gonna need it. And when you are in the middle of solving a requirement specification and you say, oh, this would be good, that would be good, oh, this is also good. Or perhaps when you're writing the requirement specification, wouldn't that be nice? Well, then you're gonna say, Yagni, ain't gonna need that. You need to sort of ask these sort of, is this a Yagni thing I'm going through all right now? Am I really going to need this? So Yagni will help you sort of keep the stuff a bit cleaner. Don't do too much thing. KISS is another way to doing this. Keep it simple, stupid. If you can solve a task in 2 ways, the hard way and the easy way, okay, let's do KISS. And this says, well, I'm going to take the small path to it. I'm going to keep it simple, stupid here, just so I can move on. So that's KISS. The third one there is telling us, don't overdo things, don't over engineer stuff. It's so easy when we are in the middle of a process and we want it to be good and nice and have all the colors of the rainbow. It's not really what was stated in the specification, but we're getting into it so much that we really enjoy it. But do not overdo it. You are doing over engineering. You're doing stuff that is basically not needed. You should not do that. The Pareto principle, or 80-20, that is basically, it's a generic principle, and it's saying something like that we could relate to that 80% of our users, 80%, so the clear majority of all our users, they will only use 20% of our features. That really makes sense if you think about it. We do applications and we put in a lot of nice features, but what is the actual usage for this application? Well, sometimes or many times the Pareto principle is sort of quite adequate to use in these things. 80% of the users will only use a small, tiny bit, let's say 20% of the application's feature. So that is also something that's sort of helping us stay focused when you do problem solving. Don't problem solve too much. This bike shedding, the last thing here, is a philosophy, and it's basically saying that when we are in a group and we discuss things, the easy problem, the easy to understand and grasp and discuss around, they get disproportionate attention. They get so much attention they should not have when we relate it to the real hard problems. And the story about behind bike shedding is sort of an organization have a meeting, they discuss thoroughly how they're going to repaint the bike sheds where the staff put the bicycles. So they discuss that a lot because it's very easy to have opinions about it. But then they get to the next agenda point that they're going to sort of, yeah, we're going to approve a lot of a million or billion money here to build a new nuclear plant. And then not so much discussion because it is such a hard task to grasp. So we don't tend to give that maybe that amount of discussion. So bike shedding is just a way to know that we are. I do think that now we are discussing a very easy problem, and we give this disproportionate weight and attention. So we could sort of stop discussing this. Is this really this important? Bike shedding. Good to know. So on we go, and I'm gonna have these tools and methods, and they are 4. So let's go with top down, bottom up, pseudocode, and flowcharts. And these can be most useful when we go in and we're gonna sort of solve a programming problem that we have at hand. Let's start with the top down, which is sort of saying that we are going onto this system on a top-down level. So we start by formulating the whole overview of the system on the top level. What is the sort of the greatness that the program is going to do? What on the large scale? And then we sort of define a few subsystems on the high level. We don't describe the details of the subsystem. Perhaps we would just put them a label on the first level. Okay? And then we take each of these subsystems and divide them into smaller pieces and smaller pieces. And eventually, when there is no smaller pieces to divide them into, we describe them in detail. And so we do that for the whole system, from the top level to the bottom level. And when we are at the bottom level, we have all the subsystems sort of refined in greater detail. And when we are there, then we can start building this system. So the top-down approach starts with the big picture. And then it breaks down from there into smaller segments until all the small segments are there and described. The bottom up is working from the other way around. Then we have all these small bits and pieces available, and we are sort of building them so they are working on their own, and then we are tying them together. We tie one piece to another piece, a 3 piece, and a 5, 7 pieces together, 20 pieces together, and eventually we have a whole larger system built up on all these sort of small pieces. So we can call it the seed model. We initially start with very small modules, but eventually it grows in complexity and completeness. So that is the bottom up. We have all the small pieces. So bottom up starts with the pieces and making each piece work before combining them into larger and complete systems. So 2 different ways of approaching on a system level how we are going to build this system level. So we have top down versus bottom up. Top down sort of emphasize the planning and the complete understanding of the system before moving ahead. We could basically say, well, if we can't do coding until we have a sufficient level of detail in our design, we need to understand all the sort of bits and pieces and the small subsystem. Then we can start coding. The bottom up, on the other hand, sort of emphasizes coding and early testing. We're building these small pieces, we code them, we test them, we make them work, and then we integrate them to build them up then. So here we can start coding as soon as the first module has been specified. So what are good and what is bad here in top-down versus bottom-up? Well, it's no bad or no good. These are just 2 different ways of approaching a system when we're trying to solve it. So it's problem solving. And when we are doing this in real life, modern software design, we usually combine these two sort of techniques to work. So it a bit depends on, but it's good to have them. Okay, I know what top-down is, and I know what bottom-up is, and I know what I'm currently working on, what type of strategy here. So let's move into pseudocode. And this is pseudocode that we could use when we are defining one of these small subsystems. So pseudocode is like write the normal language and express the programming code that is to be written. But for now we are on a high level, so we use normal languages. This is sort of we can write down a plan for the code on a higher level. This makes it rather easier to explain or design a more complex algorithm without going into the actual sort of source code or the actual programming language. We can write this on a high level that works for any programming language, basically. So it's it's like sketching on some type of dummy code or skeleton programming, and there is no broad standard for pseudocode. So it's just go ahead, write it as you feel with your normal language. Here we see a few variations of this pseudocode. So we have and we can also see here that depending on what target language I will eventually go into, there might be sort of different ways to write this pseudocode. There are no sort of standard for doing this. This is just to try to get on a higher level than the actual code will be like. So here were some examples on Fortran, Pascal, C, and Basic. So there are no pseudocode standard, but I did find a really good document there that was called Pseudocode Standard. It was a good document and it showed a lot of examples, and it also related to what was good and bad when it comes to pseudocode. So let's review a few of those examples from that document. So let's start with these here. So there's a good and less good pseudocode. So if we go from top, extract the next word from the line. That is good. And then he says, set word to get next token. That is poor. It looks a bit like he's proposing this English natural language. Use that instead of going into your programming mode. The middle one there, append the file extension to the name. Good. And not so good is name equals name plus extension. That is not a natural language. That is a bit too much programming language. And we are talking about pseudocode here, so go with the natural language. And here we are at the bottom there, for all the characters in the name, do this. Okay, good. For character equals first to last. Okay, that is okay. It is not sort of bad thing, but maybe the other one is better. So just to give you a hint on what type of pseudocode you should be writing. So try to stick on the high level and don't get into sort of details with a sort of coding constructs. You can do that later on. So pseudocode constructs, basically you will go very far with only these. So sequence, that is a linear progression where one task is performed and then comes another task and then comes the third task. So that is a sequence of tasks. I could call it statements if I was in a programming language, but let's keep it a sequence with tasks. A while loop, so repetition. So with a simple conditional test at this beginning, so do this until this happens. If then else is a sort of a decision selection, so the choice is made between two or many courses of action. So we can go a long way by doing this. Here is an example how the sort of sequence could be defined, and here we also see that we could use begin and end to be very obvious how this is going to look like. And let's read this sequence. So this is read the height of a rectangle, read the width of a rectangle, compute the area as height times width. So this is a good example of what we're talking about with pseudocode. Here you find a bit more actions. Can be like read, obtain, get, print, display, show, compute, calculate, set, init, increment, bump. So these are the type of actions that we can sort of write down in the sequence. Here is an example of how we could write if and else, and you see that he's using capital letters for if, then, else, and if, and then we have this sequence of tasks that we are grouping within them. Same with a while, we have a condition, and then we have a sequence, and we're very explicit. This is the end while down here. We can also do sort of a case. So case is, well, is a more or less the same as an if else, a specific case of it. Let's say a specific case of an if else statement. So case, this expression of, and then we have condition 1, 2, 3, or other end case. We have the repeat until, so it's specific different, well, it's a while loop, but it will always enter it at least once. So this is repeat the current sequence of tasks until this condition is done. This is a for loop, could also be useful in pseudocode then. So here we have the for iteration into the bound, and then we have a sequence of actions or tasks, and then the end. So here we have then for each month of the year. That is good. For month equals 1 to 12, okay. For each employee in the list, good. For employee number equals 1 to list size, okay. We take that also as an okay. So examples on how to write good and better pseudocode. And now we have a lot of constructs here that we can use. We can also have this nested constructs, of course, is just to tab it in, and well, most or many programming languages are constructed with this tab in, so it's easy to read. And it's also easy to read when you don't know programming languages that much. So even lesser skilled programmers can most likely read this type of sort of pseudocode we have here. If we are going to use, if we're going with sub-procedures, we can use them like this. So we are calling a sub-procedure. We don't say what type it is. Is it a class? Is it a function? Is it a module or whatever it is? I don't care right now. It is just one sub-procedure that I'm calling, and I expect to get some kind of sort of returning value maybe, or I send in some kind of parameter argument into it. So let's use call for that. Of course, exception handling could also be done. Special cases, exception handling, what should happen when something fails, and then we could write this pseudocode like we see here with the exception, and when this exception type happens, and what kind of statements or actions we are going to do there. So if we put all this together into some examples, the article author is saying that, okay, this is adequate, it's okay. So I do assume that he thinks that we're going a 2-bit deep into the programming language here. It's for x equals 10, 1 to 10, but it's still, okay, it's adequate. You do think that this is a better way of writing it, so we see that we are using more natural language here. For each column of the board, if game board position is occupied, then. So it's easy to read this more or less like a sort of book. I do not need to go into my programming skills to actually sort of read what is actually happening here on this pseudocode. Here he says pretty good, okay. And this is that in this example we are taking the whole pseudocode that maybe was written in another context, and we put it in a function. So here we have a function. It doesn't do anything now because all the pseudocode is sort of commented in it, but we can still call this function, and this is good because we can build up a programming of many bits and pieces where the functions are there, but the functions only contain pseudocode. But maybe we can compile and execute the whole program containing this pseudocode, and then we have it there. And then then the next step could be to actually put in the bits and pieces that are missing, the actual programming code. And there we have sort of outlined, using the pseudocode, this is how I'm going to do it. And then we are sort of really using the pseudocode to help us produce the correct actual code. And I think this could be a good way to sort of use the pseudocode actually produce the solution of it, the code we want. So that was that about pseudocode, useful tool when sort of formulating a content into these subsystems that we talked about before, with a top-down and bottom-up way of sort of organizing the whole application. And the last thing we're going to talk about today is the flowchart. So this is sort of a diagram representing a workflow or a process. So we are drawing some kind of solution model to our program, giving a workflow of it. It could be representing an algorithm. It is a sort of a step-by-step process to solve a task. So this is a flowchart. Here we see an example of a flowchart. This is just sort of troubleshooting flowchart for the lamp does not work. So go down there and check, is the lamp plugged in? Oh no, it wasn't. Okay, plug it in. Well, it still doesn't work. Okay, I go one more. The lamp doesn't work. Is it plugged in? Yes, it is. Is the bulb burned out? Well, I don't know. Well, check it then. No, it's not burned out. I checked it in another lamp. Okay, then you need to repair the lamp. The lamp is sort of broke. So it's a step-by-step flow chart on how to sort of solve a process. Here we have another flow chart. It is a flow chart for a for loop. It could be a C-style for loop. And if we should work it through, let's go from the top there. We see this, well, some kind of pseudocode. We see the code for it. For A, B, C, D. So it starts on the top there. That is the start of the flowchart. And then we go into the rectangular box there. And then we say A is happening. And in a for loop, that is usually initiating some starting variable loop counters. So A is happening there. Then we go into B, and B is sort of a condition here. Depending on the evaluation of the B expression, we go to right or left, depending on if we get a false or true value. So let's say we got a true value here. So we go into the first loop, the first round of the loop, and then we execute D. So D happens, and then C happens. C is part of the loop there, so it's normally incrementing or decrementing the loop variable. And then we go up again and we check the B expression. Is it false and true? So let's say it's false this time, and then we go down there and the for loop has ended. So this is a flow chart just for sort of explaining how a for loop works. The flowchart is there to help us visualize what's going on, and it's there to help us understanding some kind of process. It can also be there to help us find less obvious features within the process, like flaws and bottlenecks. And these we usually find when we go sort of a bit deeper into the process of solving a task. and the flowchart will help us doing this. And in general about flowcharts, a guy called Kaori Ishikawa, and he was a sort of a Japanese very popular organizational theorist, so he did a lot of management innovations, and he has said that this flowchart, that is one of the 7 basic tools for quality control. So he did a lot of sort of processing, engineering, processing flow, but he still defined the flowchart as a very, very essential tool to use. So that is good to know. These flowcharts are used in various different ways of sort of business management, and we can have many names for these flowcharts. It's good to know when we go out there and they are sort of saying, oh, it's a workflow diagram, it's a process business flow diagram or model, and then we can relate it to, yeah, that's a flowchart basically. Good. If you have heard about UML, that is Unified Modeling Language, it has a lot of sketches and diagrams that will help a programmer sort of sketch up and draw, design a sort of program system application. And the flowchart is basically relating to the UML activity diagram. So that is also good to know. The flowchart is available in UML, but it's called another name. When we think about flowchart drawing, we could basically live with the three small parts here. So a processing step, it's in general called some kind of activity. Something is happening there. So it's a rectangular box. Something is happening. Then we have this diamond as a decision point that we go there or we go that way. And then we have arrows just to showing the flow in what direction we are going now. And this is the basics for drawing a flowcharts. Flowchart is in general drawn from top to bottom or from left to right. The sort of shapes in this, shapes used when drawing flowcharts, they are standardized a long time ago, yes. So it's both standardized both by ANSI and the ISO organization. And here we see a few of these shapes. So we have the flow line or the arrow. We have the terminal, which is the start point and end point of a program or a subprocess. And then we have the process where something happens, changes value, something is sort of processed there, and that is the rectangular box. We have the diamond, which is the decision point, where sort of conditional operation, where the program flow goes in that way or in this way. Then we have some kind of romb stating that here we do some kind of input or output, or processing them, inputting or outputting data from the flow. So these are symbols are standardized, so it's fairly easy to get a same look and feel of a flowchart, standardized back since 60 and revised like 85. So okay. When we are working with this, we could draw this on paper. We could also use a tool. This is just one of the many available tools. This is a free one and can be installed on both Mac, Linux, and Windows. So that's why I'm having it. It's free and open source. So it's called Dia, and there is the way that you can install it from. This is just an image on drawing a flowchart in Dia. Dia could be used to draw many types of diagrams, so it's a quite helpful tool when you are sort of a developer and you need to draw sketches and show to fellow programmers or project managers. This one is just a flowchart, another example then, stating, should I encrypt my mail? So we stop in at the top there. I want to send an email. Is it okay if other read it? Yes, it is. Okay, do not encrypt your mail. Okay, so no, I'm not okay that other read me. Okay, are you Are you a felon? Are you a terrorist? Okay, well, then you shouldn't use email. No, I'm not a terrorist, so I move on, and then I get this sort of like some decision tree. Have I installed the encryption software? No. Okay, do that. Have my receiver installed the encryption software? No. Okay, they should do it. Now I have the keys. Now I can encrypt the mail, and there we go. So it's some kind of sort of a decision tree, flow chart for what will happen for a particular sort of solution or problem solution we are working with. So this was just a suggestion for a useful tool that will help you draw these flow charts. And to sum everything up that we have talked about today, I started to give an introduction. I talked a bit about problem solving in general, how we could think about it, what is important when we sort of work with problem solving, just to put everything into context. And I am faced that it is crucial that we really understand the problem and do not hesitate to ask a lot of questions when you are in this sort of trying to understand and grasp the problem. Do also remember and be able to relate to, okay, are we discussing semantics now, how we interpretate the problems or the problem description? How we put this into a context. Are we discussing pragmatics? Putting the problem into context, it is supposed to be in some kind of specific context. Both semantics and pragmatics could be useful sort of tools to help us understand the actual problem. Well, eventually I showed you about top-down and bottom-up ways of looking at the whole application, how to divide it, different ways of dividing it into small bits and pieces. And when we have these small bits and pieces, we could write them up with pseudocode. And when we have all these sort of small bits and pieces, we could also visualize them using flow charts, and we could also sort of combine them perhaps using flowcharts, combine the subsystems using flowcharts. And final slide to wrap it all up, it's to be fun if you feel it's fun. So it's an AXKCD flowchart, and it's sort of a fun, it's a guide to understanding a flowchart, and it's written as a flowchart. So just to be fun. I tried to solve it, and I eventually came up somewhere there, and it's just saying, hey, install FreeBSD, and that's the fun of it. So anyway, we can build a flowchart to try to understand what flowchart really means for us. Let's leave that for now. So this is the end of it all, and I just want to say thank you for being here and listening, and I do hope that you got something from this, both these actual hard tools, techniques that I think could be very useful when you're sort of working with the problems and subsystems, but also the first part where you sort of try to relate to problem solving in a large, and that might be easier to sometimes slow down your thinking. Yes, I know how to deal with this. I'm just going to break down this large fuzzy problem into smaller bits and pieces, and it will be much clearer for me. So go ahead and do that, because now I'm going to end, and I'm going to see you soon with another session. Bye for now. Bye bye.